In this video we're going to be looking at how you can store integers, so these are whole numbers, inside a computer, so using a digital representation. To begin with, we need to look at what type of numbers we're trying to store. So we're talking about numbers such as 5, 10, -3, 4, and so forth. Okay, we're not talking about numbers with a decimal point. And we're not talking about any of the strange ones like infinity or nans. Right? So we're not talking about those ones. We're talking about whole numbers that we're trying to store. Now, what we've seen so far when we represent numbers in binary is, let's take the number 5, for example. So 5 base 10 is the same as 101 in base 2. Binary and decimal. Remembering the 1's column, the 2's column, and the 4's column. Or the 2's are the 0, 2's are the 1, 2's are the 2, and so forth. Now, that's all fine for positive numbers. But what happens when we want to store negative numbers? So, let's say we've got the number -5 base 10. How are we going to store that in binary? As it turns out, there's actually quite a few different ways of doing this. Alright, so we have different strategies depending on whether we are storing positive and negative, or what hardware is actually we're implementing it, or what hardware we're using. Alright, so there's actually different types of forms which are more efficient in different types of hardware. So the first one we're going to have a look at is what's known as the true magnitude form. Right, in true magnitude form, a signed binary number, the most significant bit is what's known as the sign bit. So if we take a unsigned char, a signed char in true magnitude form. So remembering signed char is 8-bit. Alright, so we've got the bits, and I'm just going to number them 2, 3, 4, 5, 6, 7. Most significant bit is the sign bit. And the remainder of the bits are read exactly as per binary. So true magnitude basically meaning that we can read all of the bits as we normally would, i.e. like we do up here, but the most significant bit is a sign bit. So a couple of examples. 5 would be as a signed char 0, 0, 0, 0. Remember, I like to have that gap in there, 0, 1, 0, 1. Whereas -5 would be equal to 1, 0, 0, 0, 0, 1, 0, 1. Remembering, this is the sign bit, and this is the magnitude. So we see that if sign bit equals 0, the number is positive, and if sign bit equals 1, it's negative. Alright, so that's a fairly simple strategy, and it gives you the advantage that it is easy to be able to read without actually a computer having to decode it. Remembering this is a signed char or integer. Okay, and I might say integer in this video, but I'm really talking about 8-bit variables. In an unsigned char, right, 5 equals, as you'd expect, minus 5, right, there's actually no equivalent to that. Alright, what will actually happen is it will turn out looking something like this, which in binary is going to be 128 plus 4 plus 1, which is equal to 33. So you see that we end up with this problem that although you've entered minus 5 into an unsigned char, it's actually been represented as a much larger number. Alright, so you've got to watch out. If you're comparing numbers, especially in C, and you've used unsigned and you're trying to check for negative numbers, you're never going to get a negative number because everything just rolls over the other side and becomes larger numbers. Alright, so assumed always positive when working with unsigned versus signed, it's assumed it can go positive or negative. Alright, we can use both forms. As it turns out, the true magnitude form is not very efficient in terms of implementation in hardware. And one of the more efficient methods is what's known as ones complement. And remember, efficiency in hardware dictates power usage, which dictates speed and all the other things that we want our digital circuits and computers to be able to do. So it makes sense if we can use a different number system that's equally understandable by the computer and works faster, then it's a better form. So an alternative to true magnitude form is ones complement form, where a negative binary number has a bitwise not applied to it. In other words, the complement, which in C is the little tilde, of its positive form. So let's have a look. Take the number, and we'll follow the same examples again, 5 and minus 5. So we've got 5, okay, that's in decimal. Let's convert that to binary. Okay, and I won't be lazy, I'll do all the bits. So that's base 2. And then, because it is already positive, in ones complement form, which I'm just going to abbreviate here as ones complement, that would be the same number. Alright? Now, let's have a look if we had minus 5. Once again, in binary, it would look something like that if we took the absolute value. Okay, but because it's negative, we're going to take the complement. And the complement means just invert every single bit. So in this case, we would get 1, 1, 1, 1, 1, 0, 1, 0. And this would be the ones complement form of minus 5. Alright, so if the number is already positive, no complement applied. While if it is negative, then we take the complement of it. Alright, and if we have a look at the number line and how this would look, from 0, 1, 127 to minus 127, minus 126, and then down to minus 1. Okay, 0, as you'd expect. 1, remember nothing changes if it's a positive number, so as we're used to. 127, looks like this. And we're missing a bit. Alright, so we can see that's the largest number that we can represent. Although we have 8 bits, and you'd say, oh, well, that's 255. No, because we're using 1 bit, as effectively it's becoming a signed bit, sort of. It means that when we want to represent negative numbers as well, yes, there are 255 numbers that we can represent. Be careful, 255 is correct here. We actually have plus and minus 0. What we end up with is that we can have a smaller range overall, smaller magnitudes that we can represent. So minus 127, just invert all the bits. Okay, same thing applies if we were to do minus 126 and then right through to minus 1. Alright, so with 1's complement, that's how the form exists. The final form I want to look at, which is actually the one that's used in virtually all C compilers and computers, is the 2's complement form. And this is the most efficient. Alright, it's more efficient than 1's complement, and it actually allows us to have one more number. We can actually represent 256 numbers using 8 bits rather than 255. And we'll see why shortly. But if we take examples from before, let's take minus 5. Alright, 5 would look exactly the same rules apply. Minus 5 in decimal, okay, the absolute value in binary, same rules that we applied before for 1's complement, so very similar. Okay, we'll do a bitwise not, so we'll complement it because it's negative. So we get 1, 1, 1, 1, 1, 0, 1, 0, and then the last step, plus 1, okay, in an unsigned sense, we add 1 to it. That's the 2's complement difference. So we get to 1, 0, 1, 1. And so this is the 2's complement form, and this would be the 1's complement form. So really the only difference is adding 1 there as that final step. Alright, so we always do that when we operate with negative numbers, okay? Only negative. Because remembering, if it was positive, we would not take this complement stage, and that would be the final result, if positive, versus if negative. And the advantage of this system is that we can actually have the same algorithm, same hardware for performing basic mathematical operations, whether or not the unit is, or whether or not the numbers are signed or unsigned. Right, so you'll actually find that the signed numbers generally are represented using 2's complement form. So let's have a quick look at a few numbers using this strategy. Okay, we'll just have a look at a couple of them. What we'll find is that in traditional unsigned, and I might do that and just break that there. So we've got unsigned, we've got our true magnitude, which has the sign bit associated with it, and we've got our 1's comp and our 2's complement. So in an unsigned sense, very easy, and I'm just going to use 4 bits here just for example. Nothing changes, alright, but we cannot represent negative numbers, alright? They don't exist, we get that rollover effect, but they end up coming back as a larger positive number, which is not good. When we have a look at the true magnitude form, remember positive numbers stay the same. However, look what happened here. We have two definitions for 0. 0 positive and 0 negative. So we're basically wasting one of our combinations on a negative 0, which mathematically makes no difference. Alright? And then remembering that it's the same in the true magnitude, so the least significant bits and the 1 and the most significant bit indicates whether it's positive or negative. In terms of 1's complement, okay, nothing changes for positive numbers. For negative numbers, alright, take the positive value and remember the 1's complement rule, complement everything. So 1, 1, 1, 1 is negative 0. Complement everything, 1, 1, 1, 0, 1, 1, 0, 1, and so forth. Alright, so that would be the 1's complement form. And the 2's complement, we actually have only one definition for 0. As we expect, 0, 0, 0, 0, positive or negative 0. Positive numbers stay the same. Negative numbers, okay, the same as 1's complement, but we just add 1 to them. Right, as you see here. So plus 1 to go from here to here, and this is a complement to go from here over to here, obviously being from the complement of the positive form. Alright, only other thing to watch out for in all binary numbers, okay, regardless of form, is if we had the number 1, 1, 1, let's do 0. Okay, so in binary that would be 14, 8 plus 4 plus 2, plus 1 would go to 1, 1, 1, 1, which would be 15, plus 1 again, and we go back to 0. Right, and this is what's known as overflow. There is no saturation arithmetic built into most of these units. Once you reach the top value, it rolls back to 0. Alright, and so watch out for that. Same thing would occur if you then tried to roll over from these forms. You'll end up going from negative over to positive. Okay, so it can cause lots of horrible errors in your algorithms. So be careful. Overflow is a problem when you've only got a limited number of bits. Alright, so quick summary of what we've looked at. Okay, digital representation of integers, we're talking about whole numbers. When we've used our normal unsigned form, normal binary form, which works fine for positive numbers. However, when we move over to negative numbers, okay, there's no luck. We have to use a different form. And the way we use is what's known as a signed form. Okay, using true magnitude form is one option. Alright, where the most significant bit forms the sign bit. 0 is positive, 1 is negative. The remainder of the bits are read just as though they're in binary. And just for example, if we try to do things as unsigned, we would end up with a rollover, which would not be what we want. And 1's complement form, which is a bit more efficient. Alright, if it's negative, we take the complement of the absolute value in binary, and that gives us the 1's complement form. And we did a small number line associated with that. And 2's complement is the same again, except we add 1 to that complement form, remembering only if it was negative. Positive, it stays the same. And this version was actually much more efficient for implementation in hardware. And we did the table showing a small number line showing the differences between them, noting that everything up here is the same between forms. So same for positive, different for negative numbers. And then just watching out for that phenomenon known as overflow.